Hello, this is Brad Strabig, and I'm going to be talking about engineering sustainability using the engineering sciences, particularly math and chemistry, as well as some physics, for this chapter, Chapter 2. In this chapter, we're going to be addressing the fundamentals of sustainability science. So if you're a piano player or musician, this would be like practicing your scales. It may not be the most exciting part of our book and study and course, but without it, you really can't progress onto the stage of improvising and being able to work for yourself in the field of engineering sustainability. So you have to practice this material and get it under your belt, know it very well in order to move forward. So it's very important that you keep up with the homework problems that are assigned and keep up to date with this chapter because this will provide the foundation for everything moving forward. I was watching a baseball coaching film by Cal Ripken the other day, and he said the same thing about baseball players. You practice the fundamentals every day. This is really the fundamental science of environmental sustainability and engineering sustainability. So we'll be practicing these skills pretty much every day from here on out. A note about how to do homework. Many of you have probably seen this before. In the engineering sciences, there's a convention that's used for people to review your work. Whether it's on engineering paper or a plain white sheet of paper, you should have your name on the upper left-hand quadrant, the assignment in the upper middle, the date on the upper right, and the page number on the far right-hand side. Each problem should be named, numbered, written out, and the units should be shown in the calculations with the final solution boxed, showing the units as well. At James Madison University, one of our missions associated with the engineering school is that engineering graduates will improve the sustainability of our world by analyzing problems and designing solutions in the context of technical, economic, environmental, and social impacts. In order to understand how to analyze these problems, we have to focus on these fundamentals. Here we see some illustrations that describe how things change in systems, and it's this change in systems, dx dt, that we're concerned with. Antoine Lavoisier said he considers nature a vast chemical laboratory in which all kinds of composition and decomposition are formed. In this case, we might say reformed as well. So on the far right left-hand side, we see a picture of an early chemistry laboratory from Japan. On the right-hand side, we see a picture of the Earth's early atmosphere, in which nitrogen and carbon dioxide predominate in the very early atmosphere. In the modern atmosphere, it's actually oxygen and nitrogen and water that predominate in the atmosphere. But carbon dioxide is also very important. So we'll be talking about how things transition from one phase to another and the effects that they have throughout this chapter. The objectives for this chapter are to be able to define, convert, and determine appropriate uses for conventional units of measure in environmental systems related to sustainability. We'll look at various chemical equilibrium laws. You should be able to determine the ionic strength of a solution, the hardness of water, and what activity of a compound means and how we might employ that in different environments on the planet, depending upon where we're working. We'll look at acid-base equilibrium and talk about the impacts of acids on the environment as well. You should be able to identify basic organic chemical functioning groups, such as alcohols and alkanes, and we'll use those parameters to calculate where things end up in the environment and eventually to calculate the risk associated with chemical exposures in the environment. So pause for a minute and consider, what are 5 elements that are found in all life on the planet? The chemistry of life is fairly simple at the fundamental level. We are carbon-based life forms, which means we're composed primarily of carbon in terms of dry weight, but also by mass the largest proportion is water. Another name for water is 2 hydrogens and 1 oxygen, or dihydrogen oxide. So hydrogen and oxygen are also important components of life. Other things that make up cell life include nitrogen in the amine structures and phosphorus in our DNA. These 5 compounds are present in nearly all life forms that we know of. So we'll be focused largely on these compounds as we move through the book. So as we look at the periodic table with all the different elements and compounds possible on the planet, it's these very few elements that we'll be spending most of our time with in this textbook. We can see then that these elements are important in part because they're commonly found on Earth. Nitrogen is the most common element in the atmosphere, making up about 78% of the atmosphere, with oxygen making up 21% of the atmosphere, or 0.2095 atmospheres for a standard atmospheric condition, which is 1 atmosphere. Argon is the often forgotten about noble gas in our atmosphere, which is the 3rd most common gas in our atmosphere, followed far behind by carbon dioxide, which has a concentration of about 388 parts per million in 2014. But this concentration is changing and will be much of the discussion of further chapters of this textbook. If we look at other parts of the Earth beyond the atmosphere, including the crust, seawater, and biomass, we see oxygen is also very prevalent in all components of the Earth. Silicon makes up a large part of the Earth's crust, but we also see metals that were commonly used, like aluminum and iron and calcium. Magnesium and sodium salts, also commonly used, are common in the Earth's crust. And of course, many of these salts are also common, such as sodium, in the seawater as well, and consequently many things are common in biomass, with oxygen being very prevalent, along with calcium, hydrogen, potassium, and other compounds of importance as well. Many of these compounds that are commonly found in the environment are benign and have evolved to be used to being exposed to these compounds in the environment. Some other compounds are less common in the environment, and as a result, we have not evolved to be present with those compounds in relationship to living systems. Many of these compounds end up being hazardous or toxic to life and human life as well. The Resource Conservation and Recovery Act, passed by the United States Environmental Protection Agency, defines several hazardous materials. In particular, there are several hazardous metal compounds that are managed by this RCRA policy that was written in 1976. RCRA monitors a long list of elements and solid waste that are considered environmentally hazardous because they may be corrosive, toxic, ignitable, or flammable, or highly reactive. Also on this list, it's important to know that there are 8 heavy metals that are particularly toxic to humans. Some of these you may have read about in Sherlock Holmes books or seen on James Bond movies. These compounds are things like arsenic, barium, cadmium, chromium, lead, mercury, selenium, and silver. We'll talk about several of these through case studies later on in the textbook. As we get started, let's look and recall from your basic chemistry how we might balance chemical equations and how something simple like combustion happens. The simplest form of combustion is to take an alkane, a carbon with all saturated bonds, 4 bonds bound to something else, in this case hydrogen. That compound, carbon bonded to 4 hydrogens, is called methane. Methyl for 1 carbon, and ane meaning that it's saturated. Each carbon has 4 bonds. So we have methane. When we burn that in the presence of air, but it's actually the oxygen in the air that reacts with the carbon to form a carbon dioxide and some water. This is our classic combustion equation, where we have the methane plus oxygen going to forming carbon dioxide and H2O. The first step in balancing a combustion problem, or any organic oxidation reaction where we have a carbon compound reacting with oxygen to form carbon dioxide, water, and sometimes energy and other compounds as well. We first balance the carbon atoms. We have 1 carbon that we identify on the left-hand side of the equation, so we also need to have 1 carbon on the right-hand side of the equation. So, starting with the carbon balance, we see that the carbon is balanced 1 methane forms 1 mole of carbon dioxide. The second step, in terms of efficiency, is to balance the hydrogen atoms. On the left-hand side of the equation, we see that there are 4 hydrogen atoms associated with the methane molecule. On the right-hand side of the equation, there are only 2 hydrogen atoms associated with the water molecule, so we have to add the oxidation or combustion of methane results in the production of 2 moles of water. So for every 1 mole of methane that we burn, we get 2 moles of water. We're not quite done yet. This last step, we try to figure out how much oxygen is required to complete this reaction. So we start on the right-hand side of the equation and add oxygen to the left-hand side of the equation. So we count the oxygens on the right-hand side. There are 2 molecules of oxygen in the carbon dioxide, 1 molecule associated with water, but there are 2 molecules of water. So in sum, we have 2 molecules of oxygen from carbon dioxide, 2 molecules of water from oxygen, for a total of 4 molecules of oxygen on the right-hand side of the equation. To balance this on the left-hand side of the equation, we need to add then 2 moles of oxygen. Will combust with 1 mole of methane to form 1 mole of carbon dioxide and 2 moles of water. And it's this oxygen demand, the use of oxygen for oxidation to create energy, that we'll be concerned with throughout much of the text. So you should know how to understand and derive the combustion formula or oxidation formulas for organic compounds, or those compounds containing carbon, as they create carbon dioxide. If you follow these basic steps, you should be able to solve most and balance most oxidation reactions of carbon compounds.